Hey all, we're gonna do least squares in slightly more generality here. I'm hoping that you've already watched the least squares by example video. If you haven't, I'm gonna put a link in the description here. It's also in the Canvas shell. That's a better starting point than this. So in this, I'm gonna assume that you've basically absorbed the by example chunk. So here I have the idea that is more like the one that you're confronted with, which is you have a line and a bunch of data. In my example, I only had three data points, but the principle still holds. So my thing I'm gonna do, right, is I'm trying to fit a line through a bunch of data points. My first thing I'm gonna do is I'm gonna write down what it means to be on a line. So I'm going to kind of think about my line as C plus DT equals B again, right? And then I'm going to go ahead and write this out. So that's going to look like C plus D times T1 is going to equal B1, and C plus D times T2 is going to equal B2. And we're going to kind of continue this trend until we get to C plus D times Tn is equal to Bn. Now, I'm going to take this, I'm going to convert it into a matrix equation again. So I'm going to get a matrix equation that's going to look like this. I'm going to have some big ass matrix times a vector CD is going to equal another vector over here with my b's in it. So that's going to be B1, B2, on down to Bn there. And what goes in this matrix? Well, the coefficient on C all down here is 1. Right? So that first column is going to be all ones. And the column on D is going to actually just be the T's, right? So that's going to be T1, T2, on down to Tn. Now, you should have a solid question here, right? So what I'm going to do next is I'm going to project this B onto the column space of that matrix there. My projection formula, right, the one I'm going to use to get x hat. So what I'm thinking of here is I'm thinking A done to x equals B. This probably isn't solvable. So I'm going to sub that out for A x hat equals B parallel, right? Now, in order to get that B parallel, right, I'm going to have to project onto the column space of my matrix A. And the way I'm going to do that is I'm just going to get out my projection formula for X hat, right? So X hat's going to be A transpose A. That whole matrix is inverse A transpose times B. Like, that's just all there is to it. This is going to be like, this is going to have me done here. We're going to fiddle with this just a little bit to show you what's in there. But this formula would be done essentially. And I can pretty easily have the computer crank on this formula for me a little bit, right? The one thing I really want to draw attention to here is that X hat is the CND for your line of best fit. And I've done a projection. That projection relies right here on knowing so that I need A's columns to be linearly independent. Now, how do I know A's columns are linearly independent? Well, one of those columns is all ones, and the other one is some collection of times, right? Some t's. As long as not all of those x values, the t's, right, are the same, then we have linear independence here. Great. If all of the t's are the same, I'm trying to fit a line through vertical data. That's going to be a vertical line. So as long as my data points aren't all stacked up in a vertical line, I'm good to go with this. Cool. If I do a little bit of fiddling with my A here and my A transpose, right, I can come up with some things. Those things are going to be that A transpose A, right? So if I take this guy and kind of lay it down, right, I'm going to get a matrix that looks like N. That's from the ones times the ones, right? I'm going to end up with here, I'm going to get the sum of all the t's. And here I'm going to get the sum of all the t's. And here I'm going to get the sum of all the t's but squared, right? So that's the t's that are squared, not the sum. Okay, so that's what that piece is going to be. And I can also get that A transpose B is going to be here when I'm multiplying A transpose, right? So I've got a long narrow, or sorry, a long short matrix. And that first row is going to be the sum of all the BI's. And the second one's going to be the sum of the BI's times the TI's. And then I need to invert this matrix and multiply it by this guy. I'm sure you can see how that would help simplify things. This is not actually as easy as it's going to get. There's a way to simplify this some more, and it's kind of a pain in the ass. So you can pause here and quit if you want. The way that the computer actually does this is with this slight simplification. So I'm noticing that ATA would be easier to invert if these bits, the TIs were zero, right? The sum of the TIs were zero. So we can kind of do that. So we're going to kind of fake this a little bit. So we're just going to say, all right, this would be easier if the sum of the TIs was equal to zero. Let's fake it. So I'm going to make tau equal to t minus the sum of the TIs over m. Basically, I just subtracted the average from each one, right? So I'm going to call these tau i's and TI's, right? This is a cheater little trick, but fine. In this case, if you go back through, you'll get A transpose A is our n here and our sum of our tau i's squared. And both of these guys are going to end up being zero. And then that's relatively easy for me to invert. That's going to give me that C is the sum of the BI's over, not M, N. And that's going to give me that D is the sum of the BI's times the tau i's over the sum of the tau i's squared. And then we could parlay this into actually getting our best line. So our best line ought to be C plus D tau I, and we could rewrite that as C plus D times our, oops, that should be an I. That should have just been a tau. And we could rewrite that as C plus D times T minus the sum of the TI's over N. Hopefully this made sense. This is, again, not a huge deal. This is how the computer does it. I don't much care if you do it this way. So I care if you know how the thing works. And the thing about how it works is we take our B, we wish we could fit it on a line, we can't, so we project B onto the column space of A and then solve that equation instead. That makes our life much easier. So hopefully this is relatively straightforward. The example video is probably a bit easier to follow, to be honest.